So our next presenter will actually be talking about USB4 and what's going on in the industry, along with how do you go ahead and do you test USB4. And so with that, I want to go ahead and turn it over to our presenter. Let us begin.
Hello, and welcome to Keysight World 2020. In this session, we'll talk about USB4. My name is Jet Lim, and I'm the Strategic Planner for Keysight's Type-C technologies. USB4, USB Type-C, and USB-C are trademarks of USB Implementers Forum. Thunderbolt is a trademark of Intel Corporation, and VESA is a registered trademark, and DisplayPort is a trademark of VESA. In this session, I will provide an overview and timeline of the technology, an architecture overview, testing challenges and lessons we have learned, and finally, a solutions summary. USB4 was announced by the USB-IF in March of 2019. In just 6 short months, the spec was released in September of 2019. The reason for the very short time frame between the spec announcement and the spec release is because USB4 is based on the Thunderbolt 3 protocol, which uses the Type-C connector and bonds 2 independent 20 gig lanes into one logical 40 gig lane. USB4 also supports other standards through alt mode. The USB4 proposed electrical testing was released in February of 2020, version 0.96. Today, we have version 1.0 RC, or release candidate. The PHY electrical testing is very similar to Thunderbolt 3. We have transmitter testing, we have return loss testing, and we have receiver testing. In addition, there will be active and passive cable testing. Because USB4 is based on USB PD, you have to do USB PD Type-C testing in addition to other standards, which I'll talk about shortly. This is an overview of the USB4 architecture. In addition to testing USB4, you also have to test USB 3.2 at 5 gig and 10 gig. You also have to test USB 2. You also have to test DisplayPort over alternate mode. In addition, there's a high likelihood that you will need to have Thunderbolt 4 compatibility. In addition to that, USB4 requires that you tunnel USB, DP, and PCIe over a Type-C connector. One question we get asked very often is, if there is just one connector, what if we just test, let's say, Thunderbolt compatibility at 20.625? Can we avoid testing all the other standards? And the answer is no. And the reason is because even though there are different speeds, they all have different cable losses. This slide talks about the proposed differences and challenges between testing USB 3.2 by 1 versus USB 4. First, return loss testing. USB 3.2 by 1 did not require return loss testing. In USB 4, you must perform return loss testing. In USB 3.2 by 1, there was only one TXEQ. Pre-shoot was plus 2.2, de-emphasis was minus 3.1. In USB 4, there are 16 presets. So you must test them all, and you must also optimize the optimal preset that will be used for all future testing. This is very different from USB 3.2. To no surprise, receiver equalization is also much more complex. It requires calibration to find the optimal RxEQ to perform the long channel test. The 5-bit rate doubles from 10 gig to 20 gig. That by itself is a significant challenge. There's very, very little margin going to 20 gig over a long channel use case. Signaling is on all 4 Type-C high-speed pairs. So USB 4 always runs in by 2 mode, always. It can gear shift down to by 1, but you must ship and test the product in by 2 mode, always. There's so little margin that the CTS, the proposed CTS, requires that you de-embed the test cables. There are new insertion loss budgets for USB 4 at 10 and 20 gig, and I'll share that in the following slides. There are many new measurements. There are new phase measurements, slew rate measurements, retimer specific measurements, jitter measurements. Again, I'll talk about these in the next slides. USB 3.2 did not have crosstalk. When you do USB 4, you must add crosstalk to the measurements. In USB 3.2, understanding LTSSM was really important. Even though a USB 4 live link has LTSSM, LTSSM is not used during USB 3.4, USB 4 testing. However, you must also add common mode interference to the testing. In USB 3.2, you used a long channel calibration to test the short channel. That is not true for USB 4. You must calibrate and test at 10 gig long and short, 20 gig long and short. And if you do Thunderbolt compatibility, you must also do 10.3125 long and short and 20.625 long and short. The link optimization is done prior to the BR test. Now, some good news, because there's no LTSSM, the silicon requires that an error detector is built in. So you don't do loopback anymore. We'll query the silicon to understand what its BER is in USB 4. As I mentioned earlier, the insertion loss budgets are completely different between USB 3.2 and USB 4. Let's review the USB 3.2 insertion loss budget. That's the last row of the top table. You see the host budget is 8.5 dB, the cable budget is 6 dB, and the device budget is 8.5 dB. Now, let's switch over to USB 4 Gen 2 at 10 gig. Notice the host budget has gone from 8.5 dB to 5.5 dB. So, even though you may have designed a USB 3.2 host that works at 10 gig, that is insufficient for a Gen 2 10 gig USB 4 host that is only 5.5 dB of loss. In addition, you will notice that in a USB 3.2 implementation, you could do with a 6 dB cable. You will notice that the cable loss is now 12 dB. So the key takeaway is, even though the rates are similar, the loss channel, the insertion loss budget is quite different. So you need to be very careful of knowing that as you begin implementing your USB 4 products. The next thing that's confusing is the compliance test points. The first thing to remember is there are no set rules. You've all done testing, and they all have different test points, TP1, TP2, TP3 prime, TP3 double prime, etc. And the tables may or may not clarify to you what's the long and short channel use case. So the key takeaway to know is that there's a long channel and a short channel test case. For TX, the short channel is TP2 and the long channel is TP3. For receiver testing, the short channel is TP3 prime and the long channel is TP3. But again, don't get hung up over the definition. Just realize that there is a long channel and a short channel TX, and also a long channel and a short channel RX use case. In the next slide, you'll see a proposed transmitter test setup. First of all, there's a scope, which you should all be familiar with, and a USB 4 device, your product under test. There is the test fixture that breaks out the signals. But there is a new box that's found in USB 4 that is not found in USB 3.2. In the proposed USB 4 CTS, there is a notion of a USB 4 microcontroller. There is a USB cable that connects from a scope to the controller. There's another cable that goes from the controller to the USB 4 test fixture. In essence, all the software resides in the scope, and the scope controls the DUT through scripts that are controlled through the USB 4 controller. So command goes from scope to USB 4 cable to USB 4 controller through the SBU pins to the DUT. Now on the test fixture side, you see two pairs of outputs, TX1 pair, TX2 pair, because it's in by 2 mode, so all 4 signals, 2 TX pairs, goes to the 4 input channels on the scope. But you'll notice in this proposed method, there are signals going now to the RX pins of the fixture to go into the DUT. These are the aggressor crosstalk pins, and they are provided by the USB 4 controller. So as you can tell from this setup, it's quite different from USB 3.2 in the sense that there is a USB 4 controller and there is also a crosstalk generation that comes from the controller. And you use both TX1 and TX2 pairs for analysis. In this screen, you see the proposed transmitter test for USB 4. Some of these should be very familiar to you. For example, rise and fall times are very common measurements that are required. But this test is not required for USB 3.2. In USB 4, you must perform rise and fall time specs. And the minimum spec is 10 picoseconds. And the reason for this is, even though rise times are very important for timing and jitter, if the rise time is too fast, it will cause other problems like crosstalk and EMI and ground bonds. Hence, the requirement for a 10 picosecond minimum rise time spec. There's the usual jitter measurements, like deterministic jitter, data-dependent jitter, duty cycle, DCD jitter. However, you see there are measurements like uncorrelated and correlated jitter. So these are very different measurements that are unique to USB 4. The great news is they have already been automated and tested in the past 5 years because these are based on Thunderbolt 3. The SSC modulation measurements should be well known to you. Unit interval, a very common measurement. The common mode voltage measurement, very common. Eye diagrams, we all know how to make eye diagram measurements. The difference here is, you will notice there's the short channel eye diagram test and the TP3 or long channel eye diagram test. In that case, you have to make sure you have the TX-EQ set correctly and optimized. And of course, you need to have the RX-EQ, CTL, and DFE optimized also. There's the lane-to-lane skew test. And finally, the TX equalization. Remember, I said earlier, there's 16 presets, so they need to be tested, calibrated, and optimized. And then, of course, you have the new TX electrical idle test also, which is unique and different. This is a new test for USB 4. Matter of fact, it's so important that before we start doing TX and RX, we always do a return loss test. And the reason is very simple. If there are any issues on the PCB, on the layout, on the connector, the signal will not make it from the transmitter silicon out to the Type-C port. Similarly, if there's any issues on the layout, the signal will not make it from the Type-C port to the receiver silicon. Hence, we always make sure we do a TX and RX return loss measurements for differential and common mode return loss before we perform your well-known transmitter and receiver testing. Earlier we talked about transmitter, and then we talked about return loss, and now we talk about receiver testing. just like transmitter, there are two use cases, the no or short channel use case and a long channel use case. So what is the no or short channel use case? A perfect example is if someone was to connect a very small USB4 memory stick to your host. In this case, it's a no or short channel use case. Another example would be if a customer connected an active cable, either one with a redriver, retimer, or optical, to your product under test. In that case, it would be a no or short channel use case. The long channel use case is if customers connect a 0.8 meter passive cable for the 20 gig use case, or they connect a 2 meter 10 gig cable for the 10 gig use case. Because our customers will be using these two use cases, we also need to test to these use cases. As I said earlier, the key thing to know there's a short channel or long channel use case. Case 1 of TP3 prime is the short channel use case. Starting from the right, you see the pattern generator with PJ, RJ, and SSC. These are the well-known use cases that USB 3.2 has also. But you will notice there's the unique AC common mode. This is to couple the AC common mode noise into the pattern generator. The signal goes directly into the plug test fixture and plugs directly into the device and the test. It is the short channel use case because there's no loss from the generator to the device and the test. Now, you notice some additional things in the picture. You see words like the software channel and TX4. That is the TX EQ of the bird. So it's actually integrated into the bird pattern generator. The reason for the software channel is because during the BER test, the link optimization is formed between the device and the test and the software that controls the bird. Essentially tells the bird what TX EQ it prefers for performing the BER test. The last thing that's different is the neighbor TX. That's the crosstalk coming into the neighboring port of the Type-C test fixture. So that's the short channel use case. Now let's switch to case 2, TP3, or the long channel use case. The pattern generator is exactly the same. It's got the PJ, RJ, SSC, and the AC common mode. The TX EQ and the software channel is exactly the same. You'll notice now there are two different pieces here. You'll notice the addition of a PCB fixture and a cable. This is additional insertion loss that's used in the long channel use case. Now you'll notice in the calibration path there's a receptacle fixture. The reason is because during the calibration we need to be able to take the output of the bird after the cable into the scope, hence the receptacle fixture. But during the testing, the receptacle fixture is removed and the cable is plugged directly into the device and the test for the long channel use case. This is the proposed receiver test setup. The left is the short channel use case. And how do we know? We know because the plug fixture plugs directly into port A of the device and the test. On the top left, you see the bird, and above the bird is the common mode generator, which provides a common mode interference. And one TX pairs or one PG output pair goes into the fixture that goes into the device and the test. Now, how about a crosstalk? You'll notice that the controller adds the aggressor into the unused RX pins of the fixture, which then also goes into the device and the test. On the right is the long channel use case. And the reason it is because you'll notice there's a cable that goes from the test fixture to the device and the test. In the 10 gig use case, it's a 2 meter passive cable. And in the 20 gig use case is a 0.8 meter passive cable. So left, again, is the no or short channel use case. To the right is the long channel use case. These are the proposed receiver tests in version 1.0 RC release candidate of the CTS. To no surprise, there's a receiver eye height calibration, and you have the eye width calibration to hit the eye height, eye width targets. And of course, you also have the verification. This is especially true when you have set the instrument aside, test setup for a few days. You want to make sure when you come back that nobody has borrowed or swapped out your test cables. That's something that happens very often. So you do a quick eye diagram verification to ensure that nobody has changed your setup for the short channel TP3 prime or the TP3 long channel use case. And then you perform the test, which is the receiver compliance test. And also there's a new test here. You notice the words RX signal frequency variation testing. This is required for implementations that have a retimer. And the reason is because in a retimer, there is something called clock switch. When the retimer first powers up, there's no SSC. But when it switches to the recovered clock, there is SSC. This transient from no SSC to SSC is what needs to be measured both on the TX and RX side. And our RX side is called the RX signal frequency variation test. So if you do a large host or large hub and dock, you will need to probably have a retimer. If you do a large USB4 display, you probably need a retimer. If you do a small, say a memory stick, you may be able to get by with not doing the retimer specific tests. One of the biggest challenges you will have while performing this testing is to bring and optimize your link. What's unique about USB4 is that you actually use the sideband signals. In USB 3.2, the spec did not use the sideband signals. It is required in USB 4. So during the link bring-up, you must look at both the sideband low-speed bring-up in conjunction with the TX-RX lanes to ensure optimal link training. Otherwise, you will not be able to debug and bring up your Type-C link. This is an overview of Keysight's USB 4 solutions. First, we have the new USB 4 transmitter test software. Next, we also have the new USB 4 receiver test software. Because USB 4 is based on PD, we have also a suite of USB 4 PD solutions. In the previous slide, I talked about how you must look at both the high-speed and low-speed lanes on a Type-C active link. Keysight has introduced a new N7019A Type-C active link fixture. With this fixture, you can connect to and view all Type-C links. For example, you can look at VBus, you can look at PD, CC, you can look at USB 2, you can look at USB 3.2, you can look at USB 4, you can look at Thunderbolt 4. All signals are available using the N7019A. Keysight has also introduced the new USB 4 low-speed sideband and high-speed protocol trigger decode that runs on a scope. In addition, some of you will be implementing a low-powered version of USB 2 called Embedded USB 2. We have also introduced a new eUSB 2 protocol trigger decode software. And finally, for return loss, we have return loss software designed specifically for our VNA. When you perform USB 4 testing, there's a lot more than just USB 4. In this slide, I wanted to share with you an overview of all the testing that's required for USB 4. For some of you on the call here, you'll be doing design simulation with Keysight tools. For some of you, you'll be doing protocol decode. Some of you, USB PD. Because of the high, very fast edge rates, some of you will need to do RF testing of the Type-C connector. Channel characterization has to do with ensuring the signal paths from the silicon to the Type-C connector is perfect. There'll be tests for a sideband. There'll be tests for Thunderbolt compatibility. And of course, because DisplayPort is required for host, you'll also be doing DisplayPort testing. On the first column here, transmitter test, you will need the USB 4 transmitter test software. The scope we recommend for TX testing is the UXR, and the reason is because all scopes have noise, but the UXR adds less than a millivolt of RMS noise and less than 25 femtoseconds of RMS jitter. You also need a transmitter test fixture that will soon be released by the USB IF. And the next column over is the interconnect test. So that's return loss software and passive and active cable testing using the ENA. On the right, receiver test software that automates the calibration and testing. And also, we have the M8000 BERT, the new BERT that's less than 200 femtoseconds of RMS jitter. And that's really critical to be able to precisely test your receiver systems. And again, test fixtures that will be released by the USB IF. You also see here the notion of active cable testing. With passive cable, we simply used the ENA. It is no longer true. For performing active cable testing, the same equipment that's used for transmitter test and receiver test will be required for performing active cable testing. Thank you for your time. I hope you enjoyed the session. Enjoy the rest of Keysight World 2020. And if you have any questions, please do not hesitate to contact the Keysight team. Thank you for your time.
Thank you very much, Jip, for that wonderful presentation on USB 4. It's amazing how that technology is changing as well. I can remember just a few years ago when we were talking about 1 gigabit per second being super speed USB, and now we're up to 20 gigabits per second and moving faster. The test challenges really do seem real. It actually looks like it's a pretty difficult challenge as we move into USB 4. So thank you very much for that wonderful presentation, Jip. We really appreciate it.